Well, it's a great pleasure to introduce Spyros Alexakis from University of Toronto, who will speak on singularity formation and black hole interiors. The floor is yours.
Okay, thank you very much for the invitation. It's always a pleasure to come to Montreal. So, all right, so let me start with my lecture. Okay, I've aimed for about 55 minutes or 50 minutes lecture. I don't know how it will go on Zoom. I haven't given a proper lecture on Zoom before. If anybody wants to interrupt me and ask questions, I'm very, very happy to oblige. Okay, so I want to discuss work that I've completed a few months ago with my former student, Greg Fournodavlos. And so it concerns singularity formation inside black holes in Einstein's theory of relativity. Not everybody's super familiar with relativity, so I want to start with a very short introduction of just a few minutes. Okay, so the object of study in relativity are four-dimensional Lorentzian manifolds. By the way, you can see my cursor, right? My cursor? I guess so, okay. So where a point corresponds to an event. So if we think of this as R4 and we loosely think that there are three dimensions of space and the up-down axis is time, a point corresponds to an event, and we can think of it as it happened at some spatial coordinate x and at some time t. In general relativity, much of the physics is encoded in the space-time metric, which is Lorentzian, meaning it has signature minus plus plus plus. And the first example we can give is the Minkowski metric, which is what we see here. So we take coordinate t, x1, x2, x3, and we consider this metric on R4. It is called the Minkowski metric, and it's the analog of the Euclidean metric in Lorentzian signature. Okay, and to make it very explicit, if we have two vectors whose components in these directions are x and y, the dot product is that. Okay. So in particular, it makes sense to take the dot product of a vector with itself, and there's three types of vectors. At any point, we look at a vector and we consider its dot product with itself. If that is a positive number, it's called space-like, and that's Riemannian. We could think in Riemannian geometry, every vector has this property. But here in Lorentzian signature, you can have a time-like vector. So if you only had components in the dt direction, of course, you'll be time-like. So your dot product with itself is negative. And as you go from any time-like vector to any fixed space-like vector, in between, by continuity, you can have dot product with itself being 0. And that's called light-like or null. Okay, so we can consider analogously a curve inside our Lorentzian manifold. Let's think of just R4 for now. And a curve is called time-like if the tangent vector at every point is time-like. So at each point, the tangent vector being time-like means the curve is time-like. It's a definition. The curve is called null if the tangent vector is everywhere null. Okay, so far so good. So one of the main postulates of relativity is that matter particles can only move along time-like curves. And free-falling matter particles, ones on which no force is exerted, move along time-like GD6. Okay, so a GD6 is familiar to most of us from Riemannian geometry. It is exactly the same thing in Lorentzian geometry. So if you think of it as an ODE, in very basic analyst understanding, there's just an ODE, a second-order ODE. It's exactly the same ODE in Lorentzian geometry. Okay, so free-falling matter particles, one on which no force like a boost or somebody pushing them is exerted, but just free-falling due to gravity, move along time-like GD6. And light-like, or photons, move along null GD6. So these are some of the main postulates of the theory. And already this sentence captures the statement, no matter can move faster than the speed of light. Okay, and nothing with mass can move faster than the speed of light. It's encoded in this statement of these two postulates. Okay, now the general theory of relativity relates the metric, the Lorentzian metric of spacetime, with the matter fields that are present in spacetime. And the Einstein equations are these. Okay, so let's just take a moment to look at them. So the left-hand side sees only the metric via its Ricci curvature, and the trace of the Ricci curvature and the metric again. So the Ricci curvature is a part of the full curvature tensor. Okay, so the full curvature tensor being a 4 tensor with certain symmetries and antisymmetries. The Ricci curvature is the non-trivial trace of that. So this only sees the metric. The right-hand side is called the stress energy tensor of the matter present, and its specific form depends on what type of matter we have. We could have fluids like gases or planets. We could have electromagnetic fields. We could have Klein-Gordon fields, massless scalar fields, lots of stuff. So whatever fields you have present build up into this tensor. Okay. So John Wheeler has a very memorable phrase about this equation, which says the space-time metric tells matter how to move, and the matter tells the space-time metric how to curve. Okay, so that's the Einstein equations. Okay. It is possible to have solutions of the Einstein equations with no matter at all. Okay, so it could be there is no matter field present, and the equations then reduced by standard geometric formulas, the Ricci tensor being 0. Okay, so one obvious solution is the Minkowski space. So because the full curvature tensor is 0, but it is possible, very possible, to have metrics which are non-trivial, which are non-Minkowski, whose full curvature tensor is non-zero, but whose Ricci curvature is 0 at every point. Okay? These are called vacuum solutions, the vacuum Einstein equations. Okay. So let me start, if I can try to put one more word. So what am I trying to do now? New share. Okay, so let me make one small remark. So the initial value problem for Einstein's equations is one that is very commonly studied and is an aspect of this problem, is what we will study here. So if we consider the Einstein equations, we can define initial data for the Einstein equations on some three-dimensional Riemannian manifold. So we can take a three-dimensional Riemannian manifold equipped with a metric G and prescribe a tensor K, which is meant to be the second fundamental form of this hypersurface in the space-time we're trying to build. So this is an initial data set, which we get to prescribe subject to some constraints. And then it's a theorem that goes back to the early 50s in its proper formulation that says you can solve these equations forward in time for some small amount of time, provided the initial data is nice enough. Okay, so this is a standard canonical result. Let me say some peculiarity of the Einstein equations compared to other evolution equations. So if you prove existence in some Sobolev space typically, or in some function space, and standard local existence result tells you that for some Sobolev space for which existence theory is easy, you can solve, at least for some small time. And what can go wrong? What can go wrong is after some finite amount of time, you could reach a hypersurface. We could move forward in time where the solution, the metric G, stops being in your Sobolev space. The Sobolev norm blows up. Okay, so this is common to all nonlinear evolutionary PDE. The one thing that's a bit special in the Einstein's equations is you could consider the case where you stop lying in a Sobolev space because of singularities that have occurred in some compact region. But outside that region, the solution, let's say out here, could be very smooth. Okay, so the space-time metric G could still be very smooth. Now, a consequence of the hyperbolic nature of the equations is that you can actually continue solving around this region towards the future. So you could, just from data on this picture that I drew, continue solving towards the future. Okay? Even though there could be a singularity somewhere else, the hyperbolic nature of the equations, the finite speed of propagation, implies that you can make sense of a unique solution wherever, starting from any portion, from any domain, where the solution remains smooth. Okay? So I could continue in this region. I could consider another region here. Let me change the picture. Okay? Another picture here, and I could continue solving from here. Or from another domain there. As long as my solution was still smooth at the time t, I can continue solving. Okay. So this gives me the opportunity for the Einstein equations to consider the maximal solution I can obtain in this way. It's called the maximal hyperbolic development. And I won't define it strictly. The idea is you do this as much as possible. Okay. So if you have singularities, just don't pay attention to the singularities. Consider any open set which doesn't contain a singularity and continue solving. Okay? That is the maximal solution you could obtain. And it's called the maximal hyperbolic development. Okay. So let me motivate now my result. Let me reach our result by a historical example. Okay, so we want to speak about singularity formation inside black holes. Let me give you the first example of singularity formation inside black holes, which was published, which was found. So this is given by Oppenheimer and Snyder in a landmark paper from 1939. Okay, so they commenced with a very, very natural question. The question was, let's think about Newtonian gravity. And let's consider a homogeneous, isotropic, spherically symmetric fluid supported in a ball in Newtonian gravity. Okay, so, and consider Newtonian dynamics and consider what happens forward in time. This is your initial data, what happens forward in time. So in Newtonian theory, gravity is understood. Okay, so gravity will pull the fluid inwards, okay, will cause it to contract. By the equations of state of a fluid, depending on different types of fluid, there's also pressure which pushes outward. Okay, so there's competition. There's gravity that wants to pull in and pressure that wants to pull out. So that's a very complicated question. What will happen? It depends on the fluid. A special case are fluids of zero pressure, whose pressure is zero. In that very special case, in Newtonian theory, it's clear what happens. You know, gravity is pulling in, but there's no pressure to push back. So it will continually contract the fluid, and all the mass will concentrate in one point after a finite amount of time. Okay. So the question they asked Oppenheimer and Snyder, what is the analog of this phenomenon in general relativity? Okay. So question is, what happens to the fluid, but also what happens to the space-time? In Newtonian gravity, there is no space-time. There's only the fluid. There's only space. Right? But in general relativity, the fluid will evolve in some way, but also the space-time, the Lorentzian metric on which it lives, will also evolve. So this setting, again, for a homogeneous and isotropic fluid, rotational spherical symmetry, okay, and fluid of constant density, and zero pressure. So this is one of the very rare cases in Einstein's equations when you can explicitly solve the equation, completely explicitly write out the solution. I don't want to write out the solution for you. I prefer to show it in a picture. So let me show it here. I've given the whole thing away somehow, but okay, let's start with the initial data. So the initial data will consist of two portions. One is a portion of space of R3, where the fluid is supported. I've drawn that in red. And the remaining portion, which is vacuum. Okay. So the acceptable initial data turn out to be pretty much like pictured. So the fluid is supported on a portion of a sphere, on a spherical cap. So one imagines a portion of S3 with less than half of S3, let's say initially. Okay, so a spherical cap. The outside portion is a unique spherically symmetric manifold. It's called the Schwarzschild manifold, for those in the know. And they join up in the unique way that can be C11. Okay, C11, the only way for which there's no jump in the first derivative, but there's a jump in the second derivative of the metric across this boundary. Okay, so the second fundamental form is a match across this boundary. So this is the initial data, and it's the only way to produce the initial data. Okay. Now what happens in evolution? So after some amount of time, big O of 1, the size of the sphere shrinks, but the portion that's covered by the fluid on that shrinking sphere grows. So in particular, after a finite amount of time, you will have a hemisphere, the proper hemisphere where the fluid lives. And that joins up with a part of Schwarzschild. For those in the know, r greater or equal to 2m. Okay? So this fluid contracts. Space in itself is contracting, but it covers a larger portion of the hemisphere. And what happens after this, for a short amount out of this, is actually quite interesting. So I'm just rotating. I'm doing a 90 degrees rotation here of coordinates. Don't think of it as something very deep. So what happens is the spherical cap continues to contract, but then it joins up with a cylinder, a Euclidean cylinder, sorry, a standard cylinder, right? S2 cross R for some small interval, an initially small interval of time. Okay, so it's S2 cross R, and the S3 joins up with the S2 in the unique way that makes it a C11 metric. The red remains the support of the fluid. There's then a cylindrical portion, and eventually it opens up. It opens up and becomes asymptotically Euclidean, just like our initial data, or just like there. Okay, but there is the cylindrical portion. As we continue a little bit further in time, I will divulge there is a singularity happening at some time capital T. But let's go epsilon before the capital T. So what's happening? This hemisphere continues to shrink, so the density is going way up. It's good. And the cylindrical portion is dramatically expanding. Okay, it's still S2 cross an interval, but that interval is getting very, very big. Okay, so the length along that interval is getting dramatically bigger. Okay, and far, far away it continues to open up. Okay, but I'm interested in that. And as you go towards the singularity, the spherical portion of the hemisphere contracts like epsilon squared. The length of the cylinder expands like epsilon to the -1. Okay, and the hemisphere does the only thing that it can do, which is collapse like epsilon squared, like with the radius collapses like epsilon. Okay, and so in some sort of limit, there's been infinite contraction in one direction, infinite expansion in the other, and we've kind of lost track of what happened far away. That limit where it was opening up somehow was lost. It got pushed to infinity in the limit somehow. Okay. So these are time snapshots. What I presented here were snapshots at different times of the Oppenheimer-Snyder solution. Okay. Okay. Now, this was the first example. I want to link it now with other examples that have since been understood. So the first is discovered by Kruskal, or the correct thing to say is he gave a proper understanding of the Schwarzschild solution and its relation with the Oppenheimer-Snyder. So let me start with the Schwarzschild solution as constructed by Kruskal. So Schwarzschild's original construction was a manifold with boundary, okay, and there was a boundary right here. So Kruskal's extension saw that the maximal extension you could do, in a certain sense, has initial data supported on a two-ended Riemannian manifold. So you can think of a catenoid for those who study geometry. You can visualize it like a catenoid, right? It has an end that opens up towards south, and it joins up in a neck, and then it opens up again towards the future. So it actually has two ends. This is not very physical. Okay, in the world as we imagine it has one end, but here there's a two end, right? If I'm sitting far out here, I think the end is happening far, far away. The end is somehow only one, but in fact there is a neck somewhere, and if I were to continue in this way along the Riemannian manifold, I would see that there's another end somewhere else. Okay, and the evolution of this initial data set can be seen in the Penrose diagram. So I suppress the two spherical directions, so each point here corresponds to a sphere. There's the evolution that corresponds to the black hole exterior of one end, a black hole exterior of the other end, but in between there is a region which doesn't connect to the exterior regions by time-lag curves. That's called the black hole. And the space-time metric inside the black hole keeps on existing until it terminates at a singularity. Okay. There's a switch of coordinates that we can do. So the t coordinate moves along a curve like this, a horizontal curve, a space-like curve in this picture. And a level set r equals constant is exactly a cylinder. It's a perfect cylinder. It's S2 cross r in these maximally extended picture. And these cylinders, as we move closer and closer towards r equals 0, experience the behavior we saw in the cylinder in Oppenheimer-Snyder. Contraction in two directions, dramatic expansion of the remaining direction. Okay, so in fact, the Oppenheimer-Snyder solution agrees with Schwarzschild, perfectly agrees with Schwarzschild in the vacuum region. So this portion of Oppenheimer-Snyder, where there is vacuum, corresponds to a portion of the maximally extended Schwarzschild, just a portion. The remaining bit is experiences this contraction. This is the Penrose diagram of Oppenheimer-Snyder. This is the Penrose diagram of Schwarzschild in a not very nice picture. Okay. So these are two examples, and in a broad strokes, they paint a similar picture. One of a singularity formation inside the black hole, where there's contraction for sure in certain directions, and at least in some portion, the black portion experiences expansion. Okay, there's, however, the example of the Kerr solution, okay, written down in 1960, I think, which paints a very different picture. So the Kerr solution is a two-parameter family of black holes, and if we consider the maximal extension, they generalize Schwarzschild in that Schwarzschild is parameterized by just the mass. Kerr has a mass and an angular momentum. If the angular momentum is 0, it is Schwarzschild. So it's an extension of the Schwarzschild family, but the following very strange thing happens. If you move off of the Schwarzschild solution, introducing angular momentum, then the maximal hyperbolic development looks rather similar in the black hole exterior regions, but in the interior it looks completely different. So the Schwarzschild terminated in finite time at a singularity. In Kerr, where the singularity had been, you now have a perfectly smooth metric. And the maximal hyperbolic development stops much, much, much further down in a Cauchy horizon, where the metric is actually smooth. The metric extends to the boundary smoothly. Okay, it's just the maximal hyperbolic development. You can't continue forwards from this point of view of uniqueness of the initial value problem. So this example shows you that the singularity that you see explicitly in Schwarzschild is unstable. You can introduce the tiny perturbation of the initial data, and the singularity will completely go away. Okay. So that paints a somewhat confusing picture. This led to some conjectures, which I will get to in a minute, but I want to make a connection of these features, singularities inside black holes, with the Big Bang singularities that are also of great interest. Okay, so these are different from the black hole singularities in that one considers space-times which commence with a singularity. There's an initial singularity, and then space-time evolves from that one. Another way to view it is space-time is a Lorentzian manifold, so you could start at some time 1 and start moving backwards in time, okay? And then you would encounter a singularity, right? In finite time, you would hit a singularity. That's what the Big Bangs are. And let's start again with the first known example, which is known as Robertson-Walker. Now it's usually called Friedmann-Lemaitre of Robertson-Walker. And they concern Einstein's equations coupled with suitable fluids. And the metric is defined for positive times, and it looks like this. Okay. For some fluid that I'm not divulging, it looks like this. So let's note the spatial dimensions, the spatial directions, the spatial components of the metric shrink to nothing. They shrink to 0 when time goes down to 0. Okay? And in fact, in a perfectly isotropic way. What I've written here is, let's think of the spatial topology being R cross R cross R. If you prefer, you can think of S1 cross S1 cross S1. Okay, it's up to us. Okay. There's also fluid whose density also blows up as we go back in time. I'm not writing the fluid here. I'm more interested in the spatial geometry. Okay. So these are examples which see contraction as you go, contraction of all directions as you go towards the singularity. And they correspond to Big Bangs. They are initial singularities. In fact, these were generalized by Kastner, who found an explicit family of solutions in vacuum. And his explicit family is given by this. Okay, minus dt squared like that. That's somehow a gauge normalization. And then the three spatial directions behave according to these three different powers of t. And the Einstein equations impose two restrictions on these three parameters. So restriction 1 is this, restriction 2 is that. Okay, so we have three parameters and two restrictions, so somehow we think of it as a one parameter family. You will note that in vacuum, these equations imply that necessarily one of the three q's must be negative. Okay, it's immediate, but from these two equations. Okay, so in particular, in vacuum, there must be expansion. One of these three, the negative one, must experience rapid expansion. Okay, so these are examples. And so I say the FLRW solutions have a fluid presence, which excludes this possible expansion. But in vacuum, you have this. You have these solutions. Okay, so I'll give you some examples now of beautiful results that have been proven that go beyond this special, explicit family of solutions and try to understand their stability. Okay, before I get there, let me just mention that physically, the initial Big Bang singularity and the final singularity inside the black hole play entirely different roles in the universe. However, mathematically, they're not so different. And the reason is that the equations remain invariant under time reversal. So if you could cook up a solution of black hole type inside a black hole, you could imagine reversing time, and you could imagine constructing such a solution for a Big Bang type singularity. Okay, so the study of these two is actually quite linked. The mathematical study of the equation is actually quite linked, just because the equations remain invariant up to switching of time.
Spyros, just wanted to ask, so recent papers by, let's say, Kleinerman and Rodnyansky, who study stability of FLRWs, this is kind of related to what you mean, yeah?
This is very, very related. It's actually a Rodnyansky spec, and that's the next slide.
Okay.
Yeah, right. So that's exactly what. So that's exactly what I want to say next. So let me refer to this paper of Rodnyansky and Speck, who studied exactly stability of FLRW, moving backwards in time. So a natural question about the stability of the singularity is, if I look at the data that I have at time equals 1 from one of these special solutions, and I perturb that, let me try to solve backwards in time and understand what happens. Okay. So there are two results of Rodnyansky spec, or maybe three actually. So, but let me highlight this one. So, for some particular matter model called the stiff fluid, they showed a sort of stability result of this singularity formation in the following sense. So, you impose the same gauge you had before, and you solve backwards in time, and you see these asymptotics, where the rates of the behavior of these two things, these three things, are dependent on the point where you go. Okay, so the powers Q1, Q2, Q3 satisfy the Kastner relation, but they depend on the point you're going on S1 cross S1 cross S1. Okay, so in other words, at each different point on S1 cross S1 cross S1 to which you go, you converge to a different Kastner. Okay, a Kastner solution, but a different one, or a generalized Kastner it's called, a different one for each point. Okay,
and how explicit are these things? This is just existence results, so it's very difficult to write down explicitly these QJs. Q1, Q2, Q3.
You just know that there exists. So they don't, these are not explicit constructions of solutions. They show that all perturbations with a stiff matter model satisfy this, and you just derive that they exist at each point. There's a new result, actually just 2 months ago by Fournodavlos, my former student, and Luke, who show that something like you can choose any functions you want here, okay, which satisfy the Kastner relations, and then prescribe that as asymptotic data on the singularity and solve off of that. So you could actually have any you could have any triplet of functions which satisfy the generalized Kästner condition. So there's no relation. In short answer, there's no reason. Suppose these numbers are whatever 1/3 or 1/6, 1/6, 1/6 at one point. Then nearby there could be absolutely anything. There's no constraint that, okay, if I'm like this at this point, then the value should be that of the next point. It's not like that. There's complete freedom. Okay, and by the way, this huge contraction would suggest that there's a singularity, but okay, one can't be sure. I mean, but one checks that the curvature center blows up like t to the -2. So there's definitely singularity, right? So if the curvature blows up, then the...
So then presumably it could be interesting to see where, like, the set where q's are 0, which is sort of the boundary between expansion and contraction, no?
The space where q is 0, which is the boundary between contraction and expansion. So this particular result that I mentioned is a perturbation off of the homogeneous FLRW. So they're all contracting. Okay.
Okay.
Right now, there's a stronger result in vacuum, but in very high dimensions, where you allow some expansion. There could be some expansion.
Okay.
Yeah. And there's no particular difference. There's nothing particularly special about whether there's 0, whether the power is 0. Okay, but there's a regime. It's a perturbative result. They're always perturbative result. They can't go much further somehow. So actually, you can ask me this again at the end, because I'll link it a tiny bit with what we're seeing inside the black holes.
Sure.
Okay, let's go back to the black hole picture. So we've given examples which are quite different. Quite what one observes is actually changes a lot, right? So one is guided by a conjecture, not a result, not a theorem, but a conjecture, and that's due to Penrose in the 1970s. And a formulation is that generically, if you consider initial data with reasonable matter fields and look at their maximum hyperbolic development, if there is a black hole forming, then in the interior of the black hole, generically, the metric will end at a terminal singularity. Okay, it's just that. So it doesn't predict what the singularity would have to be, the nature of the singularity in any way. It just says that the solution ends in the sense that you couldn't construct any solution past it, even in a weak sense. Okay, so it's a bit loosely formulated. Okay, so for example, it says that what we saw in Kerr, in the precise Kerr solution, that's the exception. Okay, and in general, you should terminate at a singularity. There's a strengthened version of this, also given due to Penrose, which says that generically the singularity should be space-like, and it should also involve collapsing in spatial directions. So this is strengthening more in the direction of what we saw in the Schwarzschild example and the Oppenheimer-Snyder. And let's do a fun interval now. So this is widely believed. So here's a 1-minute intermission. So there was in 2015 was the centenary of the Einstein equations, and the BBC had a quiz, an online quiz on how much you know about black holes. Okay, so I took the quiz, and one answer I got wrong. So here's what I got wrong. So when a star collapses into a black hole, all its mass gets squeezed into, okay, the singularity, the event horizon, or another dimension. I thought it was the event horizon. But the BBC said the singularity is the correct answer. That already tells us two things. The BBC believes that there is a singularity, okay? And the very word squeezed implies that it sees that there's contraction, spatial contraction somehow, okay? So the BBC believes the strengthened version of the conjecture. There was actually a video posted on the BBC just last week, but I don't have the link here, and a whole video which also speaks about expansion in a third direction. Okay, so if you Google the BBC and somehow some black holes, you'll find the video which tells you what is expected to happen. Okay, so this is evidence that this scenario is widely believed because it even made it in the news. So
has Hawking supplied the answers to the quiz, or
I don't know if he took the quiz himself. I'm not sure. Maybe he I don't know. Anyway, okay. So there's also other predictions which I'd like to present, and one goes back to the 70s, And it says that all the examples that we've seen are actually not the generic picture. The generic picture is infinitely wilder. And this prediction was made for Big Bang singularities. But you can extrapolate it to black hole interiors because of this invariance under time reversal. Okay. So it's called Mixmaster, a term due to Misner, okay, but it predicts a chaotic behavior. Belinsky, Khalatnikov, and Lifshitz, who, by the way, if you mentioned Hawking, I can't resist. So there's this movie about Hawking called The Theory of Everything. It came out, I don't know, 4 years ago. So in his thesis defense, there's somebody with a Russian accent from the then Soviet Union who asks some questions and says the young man has done it in the end. I believe that is Khalatnikov, okay, whose 100th birthday was celebrated in Moscow a few months ago. He's still around. So okay.
Great.
So right. So generically, the space-time metric should actually oscillate widely. It shouldn't have a limit when you go down, like we saw in Rodiansky spec, for example. But it should oscillate between different Kastner solutions, but different ones. Okay. So as there actually is no limit as you go down towards the initial singularity, but you're always oscillating more and more rapidly between different solutions, each of which is a member of the Kastner family. So this is for black holes. The original conjecture was for Big Bang singularities. I should say it's based on physical arguments. Okay, there's little rigorous evidence in favor of this. There is one paper of Ringstrom in Bianchi 9, symmetry, where for fully spatially isotropic, where the equations become described by ODEs, he proved this. Okay, so he proved you have to oscillate between at least 3 different Kastner solutions. So the prediction is that the known results are somehow special cases, and the more general result would see this wild oscillation, this mixed-master behavior. Okay.
Do you know, on the math side, there are spherical and hyperbolic versions of FRW, right? Do physicists take them seriously, or I think like some physicists do, right? But is it?
I think this is in physics. It's quite, it's rather open. The problem is rather open. So there are physical papers where do some reduction of the equation that could elaborate a little bit more. My understanding is you drop some terms in the Einstein equations and simplify them a lot. Okay, and under such an ansatz, by some considerations, you derive what we said by some physical argument. Now, in spherical symmetry, there's a lot of study of the Einstein equations in the math literature in spherical symmetry. This has not been seen. Okay, so whenever you have a PDE, whatever you're described in, the Einstein equations are described by PDE. For example, in spherical symmetry with matter models. I'm not aware that there's any example of this having been seen.
Okay.
And it's not so much, if it were true, it would be so difficult to prove. So it's not, the fact that we haven't seen it in the math literature need not mean that it's not correct. Right? It's just so, if it were true, how would you prove it, right? Right? Okay, so basically I don't want to take a position on whether this is true or not, but let me just mention that in the argument that BKL constructed, they identified some special cases where this oscillation should be turned off, should not be true, and instead you should have what they call asymptotically velocity term dominated behavior, which means 2 things. It means that you do converge to a Kastner or generalized Kastner solution at each different point, like in Rodiansky spec. And very, very concretely, the AVTD, asymptotically velocity term dominated, means that if you look at derivatives of the metric, of metric components, and compare time derivatives with the spatial derivatives, the time derivatives are much more singular. Okay, so they dominate the dynamics in a certain sense, and much more singular means this, that the spatial derivatives are like tau to the delta, for delta being positive, times the time derivative. Okay. So if I think of the energy being the potential part, which is the spatial derivatives of the energy in L2 plus the time direction in L2, asymptotically, it's all concentrated in the time direction. Okay. This is what was seen in Rodiansky spec. It is what will be seen in our result now. Okay. And it is predicted, but it's seen as an exceptional case in the broad BKL picture. Okay, yeah. So far what I've done is I've shown many predictions and shown results that paint a very, very different picture depending on the setting. Let me end with some examples. One is by De Fermas and Luke, whose first installment came out in 2017, and more have been announced, which show that for black hole interiors, if one take a generic perturbation of the Kerr solution, there is a portion of the singularity which is of weak null type. I'm not going to describe what that means. It means something very different from what we see in Schwarzschild. It means that the strength of the singularity is much weaker, but still you cannot continue the solutions past the singularity, even in a weak sense. And more related to what I will present here, Rodniansky and Speck, first in 2014, then in 2018, and they've studied the Big Bang singularities with a scalar field, stiff fluid, or in very high dimensions, more than 50 or something like that, in vacuum, where you admit isotropic solutions, where the equations admit isotropic or near isotropic solutions. They can take perturbations of these and solve backwards and derive these AVTD dynamics. Okay. Let me mention, for Rodniansky-Speck, in Einstein's equations, there's a question of the gauge in which you want to study them. Okay, and it's absolutely essential in being able to prove results. They use a CMC gauge, a constant mean curvature gauge. So level sets, you have a time function whose level sets have constant mean curvature. Okay, and that's one way to approach the singularity. Okay, I've gone slower than I expected, so let me now present our result. Okay, so it's a stability result of the Schwarzschild singularity under polarized and axially symmetric perturbations. So let me write out the Schwarzschild metric for you here. Okay, this is the standard form of Schwarzschild. Let's consider we're inside the black hole, so R is strictly less than 2m. So singularities you might wonder about these things being zero don't occur because R is strictly less than 2m. Let's say R is less than m to be very safe. Okay, so this thing makes sense. This metric makes sense, and it is very singular at R equals 0 by the picture I showed you. Let's note that it's a spherically symmetric solution, the Schwarzschild solution, but actually let's just note that there's one d phi killing field. So d phi is a killing field. And also it's axially symmetric, okay, but also it's polarized, meaning that the d phi direction is normal to all the remaining three. Particularly, there's no g phi t, no g phi r, no g phi theta component. All those mixed components are 0. That's what polarized means. Okay, so the result that we posted earlier this year is this. So if you consider axially symmetric, but also polarized perturbation of the Schwarzschild data, then you have a perturbed solution to the vacuum Einstein equation inside the black hole, and it develops a space-like singularity whose asymptotics are as follows. I take this bit to be exactly like in the standard form. That's a gauge choice, a partial gauge normalization. That's what this is. And then the remaining components of the metric behave to leading order according to these powers. And these powers are as follows. Alpha, let's take this one. It's close to 1. It's close to what you have in a Schwarzschild. The other two principal powers are close to their corresponding values in Schwarzschild. So this is also close to 1. It depends explicitly on alpha by solving a quadratic equation, something very simple. And this one still has expansion. It's close to -1/2. So it still has expansion like this. Expansion Schwarzschild. And the mixed term is more or less singular. Okay, so we can solve all the way up to the singularity. We can understand the asymptotics, the dynamics fully to leading order to very great precision. And we find them to be qualitatively similar to Schwarzschild in the sense that there's two directions of contraction and one direction of expansion. And and so in a sense, at each point, you converge to a Kastner solution. Schwarzschild, suitably thought of, agrees with one of the Kastner solutions. Okay, it's got a different topology, but it doesn't matter near every particular point. So indeed, it's this AVTD picture of BKL. So at each point, you converge to a different Kastner type solution, but it's a different one at each point. Okay. Okay, let me say a word about the result. So this is in axially symmetric and polarized perturbations. Okay, you might wonder, what if I extend the class of perturbations I look at? So in one direction, if you take away the polarized condition, the result is false. It's not true. It's not true trivially because the Kerr solutions are axially symmetric, of course, but non-polarized. Okay? And as we saw, if you perturb a Schwarzschild towards a Kerr, the singularity disappears. Okay, for the maximally symmetric, the maximally extended solution, it completely disappears. It completely goes away. So one needs to impose something. Okay, if one is to preserve singularity, we're able to do it in this setting. I want to present a few of the proof is rather long and it involves quite a few things. I want to, given that I'm very behind time, I want to present a couple of ideas and maybe put more stress on the one that I think will have very broad applicability, at least within the Einstein's equations. Okay, so let's start with axial symmetry and something special that one can use in axial symmetry, which is not, I think, been exploited as much as it deserves. Okay, so polarized axial symmetry means this. The metric splits into the d phi part and the remaining part, and there are no cross terms. That's what polarized symmetry means. Okay, so it's the 3+1 metric has a 2+1 bit, and then the remaining rotation. Okay. The Einstein equations, the vacuum Einstein equations on G are these, and they become equivalent to this system. Okay, so the log of G phi phi satisfies a free wave equation. Okay, and the Ricci curvature of the remaining part of the metric is given by that wave. Okay, is given by the Hessian plus this term of that wave. Okay, so it doesn't look like from here to there life got particularly better. Sure, you got a free wave equation, which is nicer than nonlinear equations, but then you've got this guy that looks just as bad as that and probably even worse because the right-hand side is non-zero. Okay, so it doesn't look like you won anything by doing that. But the key thing is that for completely basic geometric reasons, the second equation can be re-expressed as ODEs. Okay, and if I can convince you of that, then this system is reduced to a free wave, a linear wave, plus ODEs. If somehow I can think of these as ODEs, I can study these via ODE techniques. Okay.
And just sort of a silly question in this polarization assumption for, like, I don't know, if you, by analogy, you have metrics on surfaces and then there are surfaces of revolution which have an extra symmetry, and then geodesic flow on these guys is integrable. So this is some extra integrability that you are.
Wait a sec. The GD6, it can't be completely integrable, right? So if you have a 2+1 metric, and
but so here you of course have more dimensions, right? But this gives you like an extra integral, which is useful, right?
Yeah. So the thing is, because you really split the line, okay, the geometry really isn't here. Okay. So the GD6 that I will use, I will play with GD6 big time. Okay, but they only live in here. They don't go into the phi direction at all.
Okay.
So I'm not going to use the extra thing that you have. I'm actually not even going to use it. Which makes sense because this is really a scalar, right? Because you're splitting one direction, it's just one scalar. There's no geometry. Okay. And the remaining thing is just the 2+1 metric. So I'm going to think of GD6. Yes, correct, GD6, but only the 2+1. They're not going to spill out in the third direction at all. Okay. So let me say why you can think of these as ODEs in just a sec. So let's take GD6, exactly what Dima said. So let's take an affine vector field like this, like a family of affine vector fields like this, and let's parallel transport a remaining frame along them. Okay, so one can think of the deformation tensor of this frame. Also, if you want to think of these as level sets of E0 is normal to level sets of a function, you can think of it as a second fundamental form of some function. The key thing is that let me actually maybe do it here. So how do I clear this? Yeah, whatever. That's not working too well. I wanted a new one. Clear. There we go. Yeah, clear all. Okay. So the basic Riccati equations tell me that E0 of k plus k times k, let's say ij, right? And here there's some ij outside. This is equal to the curvature tensor 0 ij 0. And that's of the metric h, which is 2 plus 1. Okay. So normally, this doesn't help me one tiny bit, because the Einstein equations tell me information about the Ricci curvature, but there's the remaining part of the curvature called Weil, on which I don't have an explicit formula. So this isn't of particular use, except when I'm in 2 plus 1 dimensions. And if I'm in 2 plus 1 dimensions, then the Weil curvature of a 2 plus 1 metric is identically 0. It vanishes identically. So what I get is an expression for the right-hand side purely in terms of Ricci. And let's remember, for Ricci, I have an explicit formula. In the reduced Einstein equations, I had an explicit formula. So that's how the system reduces to this. I get a wave on gamma, a free wave on gamma, and I get this equation, this ODE type equation on k, where the forcing term is given by gamma. Okay, the gamma I just got here. And that's somehow the second fundamental form, in a sense, of certain hypersurfaces, and the spatial part on that second of those surfaces is given by a relation like this. Okay, let's not sweat too much. So basically, the main driver of the evolution in this way is the wave, and the remaining parts of the metric 8, the 2 plus 1 metric, are encoded by ODEs. These are ODEs whose forcing term is gamma. Okay? And this is just by using GD6, just by using parallelly transported frames along GD6. I want to stress a couple of things. One is the Einstein equations are not linear equations, and so that's why I'm writing this in this way. The metric G depends on gamma. Okay? So, right, the metric G is built out of the K and the A, which depend on gamma. So G is really a function of gamma. So this is where the quasi-linearity, the non-linearity of the equation becomes apparent. The metric on which you're solving depends on the thing you're solving for. Okay? And how it depends is given by these other relations. Okay. Okay. Let's go on. So I can look at this system, and let's try to think a little bit like a physicist, perhaps. So let's look for formal solutions. Let's not try to study it in the mathematical way with, I don't know, Sobolev spaces and energy estimates and so on. Let's just look for formal solutions. So if you believe the picture I said, the formal solution for gamma will look like this. Okay. So the most singular term will have a log r, and its coefficient is a function, alpha, to be solved for. Then there's the next order term, and then something that's big O of r. Okay. And let's look for formal solutions of this ODE. That's actually quite simple. So for ODEs, there's a well-developed theory. You have a Riccati type ODE. You have some given asymptotics for the right-hand side. And you plug those in, and you want to understand what the ODE behaves like near the singularity. That's actually quite well understood. And we can expect formal solutions of this type. Okay? If the solution exists all the way up to the singularity, the asymptotics will look like that. There will be an r to the minus 3 halves principal term with coefficients. Okay. For the principal terms k22 and k11, the diagonal term will be less singular. And let me stress, there are two directions here, two principal directions, one direction of collapse and one direction of expansion. For the direction of collapse, the solution will be like this. There's somehow no free branch of the solution. It's just one solution. If you can solve all the way up to the singularity, there's only one solution that does the job. For the direction of expansion, there's also a free branch here. Okay, so there's a principal term which comes from the right-hand side, and there's also a free branch like a homogeneous ODE, a solution to the homogeneous ODE, okay, which behaves like this. Okay, so there are a few miracles, specifically in our situation, in perturbation of Schwarzschild. And the main one, whose source I do not understand, is the following. If you were to look at the formal solution you're interested in, that you expect to see, the formal solutions you believe are really there, you obtain them by ODEs. There are these coefficients which are, this is determined by the free wave, and then whatever this value is forces the values of beta and delta. And we check that the mean curvature of level sets of R is to leading order constant. It's this, it's exactly this, okay? To leading order times rho to the -3/2 plus something which is less singular, okay? So we call this CMC for free, or asymptotically CMC for free. I didn't impose a CMC gauge, I imposed a geodesic gauge. But it turned out that in this geodesic gauge that I wanted to study, CMC came along automatically. That sounds very strange, okay? But it did happen. Okay, and I do not understand how I cannot understand it on a priori grounds. Okay, so that's one. I've condensed two things here. One is in polarized axial symmetry, the Einstein equations become a wave, like a standard wave with ODEs. And specifically in Schwarzschild, the ODEs satisfy this behavior. Okay, and they give me the asymptotically CMC property. Let me stress now some difficulties one has to face, which is a consequence of the anisotropy of what we're doing. So if you want to approach the singularity by a family of GD6, one must worry about a gauge collapse. That the choice of GD6, the choice of gauge, the choice of coordinates ultimately, will break down before you reach the singularity. So it's not really a singularity of the metric, it's a singularity of the gauge, it's a singularity of the coordinates. But if that is to happen, you will not be able to distinguish that. Right? So we want the gauge that persists all the way to the singularity. This is quite a central issue in math, even in physics, even in numerics. So people are very, very well aware of the gauge breakdown that can destroy everything, and it destroys your method, but it doesn't destroy the solution. So there's great danger of this happening here, and let me explain why. If you want to consider a congruence of GD6 that goes towards the singularity, there's great danger of focal points, or of two GD6, let's say, crossing. So this can happen even in Euclidean space. One can consider GD6 that shoot towards the origin, all right, and they all join up at the origin, so polar coordinates. The K's would break down there, but it's not that the Euclidean metric is bad, it's just the coordinates you chose are bad. Now, if you have a geometry which has a collapsing direction, that's hugely dangerous, right? Because you can imagine, right, when you're trying to shoot GD6 and the space itself is collapsing, the possibility that they're going to cross is humongous, okay? So unless you make a very, very, very wise choice, it's almost certain that if you choose random GDs and shoot them towards the singularity, they're going to cross because of the collapsing, because space is being squeezed down. So that's a big issue. Okay, so there's one way to avoid it that I know, and that is to solve this second equation, the equation for K, starting at the singularity. Okay, so assume you had the singularity and then solve backwards from it to single out the essentially unique gauge which doesn't experience breakdown, that has GD6 being separate, non-intersecting all the way to the singularity. Okay, and then one wants to do estimates and to really prove that all these formal asymptotics we have are really true. So there are two things that are happening together. One is, in order to be able to solve backwards from the singularity, I'm not going to solve the coupled system together, but I'm going to be doing an iteration. I'm not going to get to the details of everything, but somehow I'm going to do an iteration, partially solving forwards for some variables, partially solving backwards for the other variables to avoid this gauge breakdown. In this iteration, I get this asymptotically CMC property, which is terrific. Okay, I get this asymptotically CMC property for free, which is terrific, and which allows me to close the energy estimates for the wave. Otherwise, it would have been absolutely impossible. And let me mention one final danger, again, which comes up, and whose source I do not really comprehend, but let me just mention it, and I think I'll end my lecture with that. So let's look at the K11 equation, which is a Riccati equation, and whose sign of K11 is somehow defocusing. Okay, for ODEs, it makes sense to speak of focusing and defocusing. The sign of the initial datum is somehow defocusing. So we saw that there's a free branch of the solution. When I work with Sobolev spaces and so on, I also need to control all these parameters in Sobolev spaces. In particular, I need to differentiate. So let me look at the differentiated equation. It admits a free branch, right? It's a linear equation on the first derivative. And it admits a free branch by general ODE theory, which is fully consistent with the free branch I had for the undifferentiated equation. Okay, that's for the defocusing part, the easy part, the expanding part. Now, let's look at the focusing, the branch that sees the collapsing. From ODE theory, that had a unique solution. If you're able to reach that without gauge breakdown, there's only one solution that does that. But you need to differentiate that equation also. And now, the differentiated equation is linear in the first derivative, and it admits a free branch, which is way, 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 way too singular. So it's singular like r to the minus 3 almost. Okay? Whereas the leading order behavior I expect is r to the minus 3 halves. So is it conceivable that the derivative of the function is hugely oscillatory, but the function itself, the undifferentiated function, is much, much, much less oscillatory? If that were true, if that really happened, I do not know of any way you would be able to prove it. So the result, even if it were true that this really happened, you wouldn't be able to prove it. So the only hope is that somehow, while the differentiated equation admits this free branch, somehow it's not really there. Okay, so the existence of this we could call a linear instability. So the differentiated equation have an instability which is not there for the undifferentiated. So if this free branch was really there, you would not be able to prove estimates, right? So if your first derivatives are really, really singular, then there's no way to prove that the undifferentiated thing is not singular. Okay, okay. So and the way to avoid this free branch, to eventually prove that it's not really there, is to, again, since you're solving backwards, you can set this free singular branch to 0. Okay, you can set it to 0. Okay, so the grand scheme is an iteration scheme where I produce a sequence of metrics at each point. Okay, by first solving on an initial data hypersurface. In this gauge, the initial data needs to exist somewhere, and it's on a hypersurface that I need to find, I need to solve for. I'm not describing that. I then solve the free wave forwards towards the singularities, and then some of the Riccati equations are solved backwards. Okay, and then I identify the next hypersurface where the initial data should live, and I can solve for the remaining things forward and iterate. So I don't want to give any more details. I think I've tired everybody a bit too much. So let me just give a small summary. So there's the first thing I want to say is there's a new method introduced to study Einstein's equations in axial symmetry, at the very least in polarized axial symmetry for now. There's a huge wealth of results, mathematical results, physical results, numerical results, on studying the Einstein equation, this very complicated system, with 2 degrees of symmetry. Let's say spherical symmetry, or T2, S1 cross S1, or whatever. I hope that this opens up the way to kill one of those extra degrees of symmetry and go to just 1. So it opens up this new method, this new avenue to study the equation with just 1 degree of symmetry. Okay, and the key structure in this setting is a free wave coupled with ODs. Okay, if you didn't have Polarize, it would be a wave map system with ODs. So it's conceivable, I believe it's true, that you can study Einstein's equations in this gauge, and it's actually going to be simpler than other gauges in many settings. All right, so this opens the avenue. Take your favorite result, which was proven in spherical symmetry, and relax that. Take any space that you can obtain with 2 degrees of symmetry, and perhaps you can study the stability of that with just 1 degree of symmetry. Okay, and 2 other settings is the other extension we're going to hope to do is if you didn't have 2-ended initial data but 1-end initial data, maybe not describe that too much. and also open up other questions. So for example, black hole exteriors with 1 degree of symmetry, or even other cosmological constants. Okay. So that's right. So that's also all I wanted to say. I think I went a little bit over time. I can be excused due to Zoom. So thank you very much. Thank you for your attention. So that's it. Okay.
Thank you very much. I would like to thank Spyros for a great talk.
Okay. It's a weird experience, but thanks. Sure.
Are there any questions? You can unmute yourself and ask, or you can ask on chat, or so can I ask one question? In hyperbolic geometry, there is this thing called Margulis lemma, that if you have a very short closed geodesic, then there is a big collar around this geodesic where the normal map is kind of continues nicely. This, like the 39 paper described in the beginning, kind of reminded me a little bit, because there is this shrinking sphere direction, and then there is the cylinder which is getting longer. So you have like a shorter thing coupled with a longer neighborhood of size. Is there anything more general like that, or this is just very superficial? I don't know.
So I don't. I mean, the thing is, the spatial geometry is like what you said. So there's a very thin collar neighborhood, a very thin sphere, right, with a very long cylinder. But in GR, you don't really look at spatial geodesics, okay, because the ones that are naturally relevant are time-like or null.
I see.
All right. So I don't know if so I've never thought of that for that reason. Okay. Now, how geodesics behave near the singularity is definitely interesting, but the fact that it's collapsing leaves very little room. Right, the fact that this direction is that's collapsing in space to nothing leaves very little room for geodesics to.
And can one, like, sometimes you can try at least maybe in Romanian cases you can try to resolve the singularity. So like Penrose does, look at the finer resolution near this collapsing point and try to understand things better. But again, this is also very naive.
Yeah, so I know one person who was doing maybe not quite resolution singularities, more like what you do in. I know one person who more like you do in Ricci flow. So you go towards singularity, take a sequence of blowups, and you want to see what you converge to. So what he had told me is that for any of these, you get a Kastner. So you take a time-like geodesic that goes towards the point of the singularity, and if you do suitable blowups of your solution, you're going to see a Kastner. You're limiting the space-time will be a Kastner. Okay, but at each different point, it will be a different Kastner. Right. So then, because you've understood you've approached all possible points of singularity together. Right. So for each different point, it's a different Kastner. So I think the short answer is it's too varied. The singularity is too varied to do something like a Penrose type resolution singularities near, I don't know, a conical singularity or whatever. Right? It's too wild, right? So, right. That is my opinion, right?
And so, if again, very naive question by analogy. So, suppose spherical symmetry or axial symmetry, this is like some integrability condition in some sense. Yeah. So if you have an integrable system, then there are KM type results, which say that some perturbation, some invariant tori get preserved after some perturbations, in some sense. Is it complete nonsense to expect anything similar to appear, for Einstein equations, that if you perturb
Okay, I can only think of one loose analogy, but loose, very loose, which is, so in Kerr. So one Keeling field gives you some integrability, but not much. Okay. So I can think of one small analogy, which is in Kerr you have two Keeling fields, okay, which somehow give you two conservation laws for the geodesic flow, for example. Okay?
Right.
There's something called the hidden symmetry. There's an extra integrability, which was found, I think, by Carter and Robinson. Okay, so there's some sort of there's a Keeling tensor. It's not a Keeling vector, it's a Keeling tensor. It's a Keeling 2 tensor, which gives you some extra integrability, and that's how you can understand the geodesic flow perfectly in Kerr. Okay, that has been used in analysis in PDE. That has a manifestation in the analysis of the wave equation. I believe that was Blue and Lars Anderson. Right? I've heard from Kleinerman that it's very useful in what they've done. They've done a perturbation result for the Schwarzschild here in polarized axial symmetry, and they've got ideas for Kerr. And I've heard that this extra integrability is very useful in that regard. Now, I don't think they think in terms of invariant tori, but somehow it's a very useful thing in what they do. But that's all I know. I just don't know more.
I see. And is there any conformal invariance that shows up that's somehow useful in these questions, or?
In these questions, in what I just did now, no. There is something small, but it's not been, I don't know that it's been used or anything like that. So this reduced system that I wrote, the reduced Einstein equation, have a second formulation when you do a conformal change. So you can do an extra conformal change and the equations simplify even more. I didn't use that, but it's well known. So it's possible that one could use one could look at conformal invariant things. You want to do that extra conformal change to simplify the equations even more, and use some conformal invariance to transition to help you with your analysis, right? But that has not been done. I don't know of anybody who's done that. It's a challenging thing, but I don't know anybody who did it. Right?
Are there any other questions?
I have a question. Can you hear me?
Yeah, sure.
Yes.
Okay. I don't know anything about this, but I was looking up a bit about Kerr singularities at the beginning of your talk.
Yeah.
So I see a picture of them on Wikipedia. They're called ring singularities.
Yes.
So first of all, in what sense are they actually singularities of the metric, or what are those
Okay. Yeah. So I know that. Okay. So what you see on Wikipedia refers to what's called the maximal analytic extension of Kerr.
Right, I understand.
So if we look at this picture, the maximal hyperbolic development stops where I said. This is it. There's no singularity anywhere. Okay? But it so happens that the metric is real analytic up to and including the Cauchy horizon. So it makes sense to take an analytic continuation. Okay. In my very humble opinion, that does not have physical content. Okay, but nonetheless, physicists do this, and I believe it in Hawking and Ellis and so on. It is very commonly done because you can do it. Why don't you do it and see what happens? Okay.
Okay.
Right, and there are these singularities which are ring singularities. I believe they're actually time-like singularities. Don't quote me on that. I don't know anybody who studied them mathematically. Partly the reason is that they exist in this artificially constructed region. And I should also say that but I don't know anybody who studied them mathematically. And I should also say the Fermat-Luke result tells you that this Cauchy horizon, which is smooth, and the metric is smooth up to this, and even real analytic, if you take the tiniest perturbation of Kerr, this is where the weak singularity lives. So you wouldn't have been able to do that on a continuation at all. So in some sense, it's exceptional.
Okay. What kind of weak singularity occurs when you make a perturbation?
So let's say the Christoffel symbols fail to be in L2.
Okay.
And that means you can't do even a weak.
There's no metric picture of the singular set.
No, this boundary makes sense in a C0 sense. I think what's expected is the boundary makes sense. The metric makes sense in some sort of continuous sense.
Okay.
Okay, but the Christoffel symbols fail to be in L2 across such a boundary.
I see.
Okay, so you couldn't do even a weak formulation. But that's the idea. Yeah.
I see. Okay. I see. Thanks.
Are there any other questions? Well, if there are no further questions, let's thank Spyros once again.
Okay, thank you so much. Okay, so dinner in Montreal is great. Okay, so
thank you very much for joining, and see you again on Zoom.
Thank you.
All right.
Okay. Okay. Bye. Thanks.
Bye.
Thank you.